So Professor Jaramillo I've known for quite some time, and he's a real leader in the field of sustainable chemistry and engineering. He's currently the professor in chemical engineering at Stanford, and also the director of the SUNCAT Center for Interfacial Science and Catalysis, which is a joint partnership between Stanford and SLAC. He's won many awards in his career, including the PCASE Award, the Presidential Early Career Award for Scientists and Engineers, and the Paul Emmett Award in Fundamental Catalysis, most recently, and from the North American Catalysis Society, and a very long list of awards. And he's also on the annual list of highly cited researchers by Clarivate Analytics. He has been a tremendous force in the field of small molecule transformations for sustainable energy and other and a circular economy, and basically really has always been a leader in envisioning what the future can be in terms of having a greener environment and a better, I think, future for everybody. So without further ado, Tom.
Well, thank you so much, Jenny, for the invitation to be here today, to connect with the Irvine community. Solutions at scale. I can't imagine an endeavor more important given the world that we live in right now. We need solutions, we need sustainability, and hopefully I can address some of those themes today. So thank you again for the invitation, and I'll go ahead and start sharing my screen. And if I could just get a verbal confirmation that it looks okay. How's that looking? Good. I saw the thumb up. Fantastic. Thank you so much, Jenny. All right. So why don't we dive into it? So what the theme of today, designing catalysts and chemical processes for global sustainability. 3 key points. These are 3 kind of underlying messages that I'd like for you to have in mind as we kind of navigate through this space. So first and foremost, I hope we all walk away with a recognition that there really is an opportunity to innovate the fuels and chemicals industry for improved sustainability. Not only a lot of opportunity, but we've actually come a long way. We have a long way to go, but there's a lot of hope and promise. Another theme, you'll see a lot of work that I show here today that is computational and a lot that is experimental. And it's really those 2 things working hand in hand that I think is going to give us the best chance to innovate ahead. So that's another underlying theme. And then finally, fundamental science and engineering is absolutely needed. We need it more than ever. We need new ideas, new concepts. We also need to start extending ourselves into more applied systems, especially those of us who are in academia or potentially in national laboratories as well. We really need to make connections in these spaces, try to, as I see it, de-risk technology so that they're as friendly as possible to ultimately scale, which is what the Solutions at Scale Center is all about at Irvine. So those are 3 key points. And moving ahead, before we dive into all the new tech and new opportunity, I just want to take a moment and recognize one of the greatest achievements in the history of humankind, and you're staring at it on this screen. It's really the fuels and chemical industry as we know it. Let me tell you, it's not perfect. It's in fact far from perfect. But let's just take a moment to appreciate what we can do, or what we have done as scientists, engineers, those working in the policy, regulatory world, economics, finance. Really, we've got an ecosystem today in the year 2022 where we produce literally trillions of kilograms a year of stuff, of molecules, of materials, and we ship that stuff across the globe, getting it in the hands of billions of people to improve their lives for a high quality of life. And so we do need to take a moment and I think appreciate all that technology that's in the ground, as well as, again, the regulatory frameworks that govern it and the economics behind it. We're looking at a few molecules, not all molecules, but just to give a sense of scale. Here's hydrogen, which we produce at 70 billion kilograms a year. That's about 9 kilos a person per year on average. Ammonia, 180 billion kilos a year. Gasoline is about 1 trillion kilos a year. And plastics at about 300 billion kilograms a year. These are just some of the 70,000 different molecular products that we make in our society across the globe that have value and do provide a quality of life. As amazing as these things are, and by the way, as cheap as they are, because these things are like 50 cents a kilogram, $1 a kilogram, maybe $2 a kilogram. I mean, what can you buy at the store for $1 a kilogram? Not a whole lot. And yet we can make use of what we're looking at here today. There are some issues. They're not sustainable, is the first thing I would say. They're almost entirely derived from fossil resources. And number 2, they're not accessible. Those of us who are on Zoom today are probably consuming more than our fair share of the numbers that you see here per person because there are billions on Earth that have minimal access to this system. So I think there's a lot of opportunity among the many things that we can improve. Sustainability is one, and access is another, equity, in other words, really trying to improve the lives of all billions on Earth, not just some billion. So that's really the motivation for thinking about doing things differently than we currently do today. And I want to recognize a team of scholars in SUNCAT, the SUNCAT Center that Jenny brought up. We are, in fact, a partnership between Stanford and SLAC. We bring a lot of intellectual strength and tools and capabilities that a university plus a national lab can really bring together in unique ways. So about half of the senior personnel you see here are rostered at SLAC, and the other half are rostered at Stanford. And we have really a broad range of research abilities and competencies and skills. So we have a number of computational folks. A lot of our center is really founded on doing theory and computational work that really inspires experiments. And we have a great team of scholars who can synthesize a wide range of materials. The periodic table is pretty much our playground, all kinds of nanostructures, nanowires, and mesoporic materials you can think of. Characterization, not only the wonderful characterization tools you might find at a university campus, but also things like a synchrotron and a free electron laser that are very much national lab type of capabilities. And then, of course, we do the testing and understand kind of what worked and what didn't. We feed that right back into the theory to improve the physics-based modeling and wrap it all of this up with a cozy, warm blanket of data science to try to unlock deeper meaning, more insights than you might otherwise have. We're a center that is founded and rooted in the U.S. Department of Energy, Office of Science. I also want to give a shout out to our administrative staff who are just absolutely outstanding in making things run. So now, what is it that we try to do? One of the many things, or the many projects that we work on, is trying to use electricity. It's pretty clear that with renewable electricity, if you can use that as your feedstock, as a power source to do the chemical transformations that you're after, you're in pretty good shape in terms of renewability and sustainability. 10 years ago, it was a tough proposition because renewable electricity was expensive. It was like 10 cents a kilowatt hour, 15 cents a kilowatt hour. And amazingly, thanks to a lot of different forces that are pushing in the right direction, those prices have dropped amazingly down to about 4 cents a kilowatt hour for both wind and solar unsubsidized levelized cost of electricity. Those numbers continue to decline, and that really opens up the possibility of using this as a resource to do the power the chemical transformations that we need. Now, before you think that this is pie in the sky chemistry, it's actually been commercialized for many decades. I'm showing you 3 very important examples. On the left-hand side, we're looking at aluminum oxide electrolysis. Basically, every time you pick up a can of soda, where did that aluminum come from? It ultimately came from bauxite, which of course is a mineral that contains aluminum. I just write aluminum oxide here to keep the chemistry a little simpler. This is an electrified process. It's actually over 60 billion kilograms a year of aluminum that we produce. It takes about 100 gigawatts on average of electricity to power this process. It's more than its fair share of CO2, but we need it. Aluminum is a really important material, not only for cans of soda, but fuselages for aircraft and all kinds of other applications. This is an electrified process. The chlor-alkali process is another big ticket example of electrification. So this is how do we get our sodium hydroxide and our chlorine? We get it from sodium chloride, from brine, from very saturated streams of salt water, and we electrify that and make sodium hydroxide, which again, and chlorine, about 60 billion kilograms a year each. Sodium hydroxide using all kinds of chemical processes. Chlorine, next time you pick up a credit card, you're probably touching polyvinyl chloride. That's where some of that chlorine goes. And then on the right-hand side, you see water electrolysis. Actually, water electrolyzers were first developed and shown over 2 centuries ago. It's old tech, and it's been commercialized for about one of those centuries, the last century. I specifically chose imagery here of these commercial processes that are not brand new. It's been done again for many, many decades. Of course, the modern technology looks better than what we're looking at today, but it's really just to show you that there's a lot of opportunity here. We can electrify processes. We can make them renewably and sustainably. The question is, can we do it in a way that's cost effective and cost competitive with the known industries today? So that's the opportunity. That's the challenge. That is the opportunity. So how do we go about creating a new paradigm? Very simple equation. The production cost of whatever molecule you're looking to make, dollars per kilogram. Obviously, we want to be cost competitive there. It's going to be a function of 2 things. The CapEx, the capital expenditures that go into the facility that you build, and then the operational expenditures for the feedstocks and maintenance and all that kind of stuff. So I'm going to present here 4 extremely ambitious targets. We've got 1 cent per kilowatt hour renewable electricity, $10 per kilowatt hour energy storage, because chemical processes typically don't want to be on and off with the variability of wind or solar, but typically want to run 24/7, 365. If you're looking to make a carbon-based product, you probably want to grab that carbon to be sustainable from CO2, and that'd be great. And so there's a feedstock cost there of capturing CO2 and putting it into your system. And then there's the electrolyzer itself. You're putting in these feedstocks into the box. You're asking the box to do those chemical transformations for you, whether it's hydrogen from water or carbon dioxide or carbon-based products from CO2 or ammonia from nitrogen, et cetera. We need the CapEx to be low. And so the point is, we could spend a good amount of time diving into where these numbers came from. It's really a kind of top-down or going backwards, I should say, approach of what your production cost is to hit certain targets. And so the CapEx and the OpEx can only be so expensive for you to be able to stay within those limits. So that's kind of where I came up with these numbers. All of them are heavily ambitious. We're not at any of these, I should say, with the possible exception of 1 cent a kilowatt hour renewable electricity in some sites on Earth. It is that cheap. But at the end of the day, we need lots of sites on Earth to be producing enough electricity to be able to power enough of these molecular product production that it can make a difference in the CO2 emissions. So yeah, lots of opportunity for many different scientists and engineers to contribute in this space. I'll be focusing on this box on the bottom right-hand side. Now, the goal here is ultimately to create a whole new system for producing and consuming fuels and chemicals and materials in a way that is sustainable. And there are a lot of different technologies that contribute in the fabric and the canvas that we're painting for the future. I'm just trying to pick a few of them here. And the way I look at it, what do we need? We need products, we need molecules for transportation, we need building materials, we need chemical building blocks, we need fertilizers, we need lots of different types of molecules. And the goal here is to take molecules that we have in abundance and convert them using renewable processes, either direct solar-based processes or electrified processes. They can either make the product that you're looking for immediately or make the precursor that can then go into a separate process for further upgrading. So for example, you could go from water to hydrogen. That hydrogen then could go into modern chemical industry as we know it for hydrogenation processes. You could upgrade CO2 that way to make fuels and chemicals. Or you could take that hydrogen and feed it into Haber-Bosch facility for ammonia production. So there's a lot of different ways to mix and match this. And one of the key points I want to make on this slide, number one, there's lots of opportunity to innovate in this broad technological landscape. It's also really important for us to think about how this is all going to be integrated, because if we're just trying to drop in, replace one technology with another, that's really tough. I think we have a much better chance if we think about how these things are integrated in the future and really take advantage, leverage the complementarities that could exist in the ecosystem that we build ahead, not just trying to match the ecosystem that exists today. So with that, I want to give 3 examples really on the techie side as we dive deeper into the science and engineering behind this, but all of that is kind of a preamble. How can we develop systems for improved hydrogen production from water splitting? How can we develop systems for making carbon-based molecules from either CO2 reduction or carbon monoxide reduction? How can we make ammonia from M2? I just want to give you a few vignettes on how we think about this and how we approach it. We'll start with hydrogen first. So hydrogen already, as you saw, 70 megatons a year production, absolutely massive. This is where it conventionally goes to ammonia production as well as hydrotreating oil for upgraded fuels. But then the question is, can we use it as an energy carrier more broadly for heating homes, for transportation, et cetera, et cetera? There's so many possible applications. And really, it only makes sense to use it as an energy carrier if you can make it renewably and sustainably in the first place. And that's not how we currently make it. The current process is steam reforming, as you see here. You can look at the chemistry. You're feeding in hydrocarbons and you're reforming it. You get output hydrogen out and you're spitting out plenty of CO2 to go along with it. In fact, about 2% of global CO2 emissions comes from this process that you're looking at right here. And we need it because this is what feeds us. This is what provides the ammonia that fertilizes the land that ultimately gets fixed nitrogen into our body. And obviously for fuels for transportation, whether you're flying on a jet or a bus or a truck or a car or a boat, oils or petroleum products are really important as well. So the question is, can we do something more sustainable? And a very simple example, there are many possible routes, but the simplest one to envision is really coupling a photovoltaic with a water electrolyzer. Both are already commercialized and scaled. How can we make that work? Well, let's take a look at that. So what does a commercial electrolyzer look like? So here's a modern day version of ThyssenKrupp, a 20 megawatt module. So they sell this. The problem is that it's too expensive compared to conventional hydrogen. So the steam methane reforming we were looking at on the previous slide, it's about $1.20 a kilogram in the United States. And then if you purchase one of these and plug it into some reasonably costly electricity, it's down to about $4 to $5 a kilogram, which is really nowhere close to the $1.20. So the U.S. Department of Energy recently launched an Earth shot or several Earth shots with Secretary Granholm. And the goal here on hydrogen for one of the 3 Earth shots is to get to $1 for 1 kilogram within 1 decade. We need a lot of R&D to get there. So there are lots of ways to contribute to this because there's not a single lever that can, one lever alone, get us from $4 to $5 to $1. We need lots of levers, like 1,000 of them, pushing in all the right direction to lower costs. And I'll be addressing some of those today. So where do those costs come from? This is maybe a little bit easier way to look at a plant. This is coming from Proton Onsite, now acquired by Nel, for a 50-ton-a-day production facility. It's about a 100-megawatt facility for hydrogen production. And these are the electrolyzers that do the work. That's what you're feeding the water into to split into hydrogen and oxygen. But of course, the chemical engineers in the audience will know that it's not just about the reactor. You've got to design the balance of plant around it. So you need water management to purify that water to feed it in. You need hydrogen management. You need power supply. You need lots of different things that contribute to the cost. That's what's shown on the left here. And so the biggest chunk of the pie are actually the stacks themselves. These gray boxes that you see here, those are the electrolyzers. And in this analysis, a big chunk of that cost is coming from the platinum and the iridium catalysts that are in there. These are very conventional catalysts that are used in modern day PEM water electrolyzers. So that's one area of possibility to reduce cost. And so these are the 3 key needs that I want to be addressing in the next segment here is how do we lower cost of these systems by reducing or eliminating precious metals? How do we lower CapEx for water purification? Because then you can avoid a lot of this business and then operate with impure feedstocks. That could save some cost as well. And how do you couple these things to sunlight? What are smart ways to coupling to PVs? So let's talk about the catalyst first. How do we get rid of platinum? Well, platinum's tough to replace because it happens to be the very best thing on Earth, hydrogen production. But there are some competitors out there, and you're looking at 2 of them. One is nitrogenase and the other is hydrogenase. These are Mother Nature's catalysts for hydrogen evolution. And if you take a look, Mother Nature figured out a way to be about as good as platinum without any precious metals in sight. And so this is an active area of research for many across the globe. We're trying to understand how these enzymes do what they do. These are some DFT calculations that came from Barry Hinneman and Jens Norsko some years ago. They really pointed to this motif here as being an interesting one. This is an undercoordinated sulfurs. You notice that this sulfur is bound to 2 metals here, which is different from the sulfurs up here that are coordinated to 3. These show no signs of activity according to the theory, but this one looks pretty good. So this one really inspired me and others when I was a postdoc, in fact, at the Technical University of Denmark, to explore as a motif molybdenum disulfide. It's a layered material. It's really a sandwich of sulfur, molybdenum, and sulfur, and then you stack these sandwiches with van der Waals forces in between them, so it slips just like graphite. And these edges of the molybdenum sulfide actually have a motif that is somewhat similar to this, right? It's undercoordinated where each of these sulfurs is bound to 2 mollies as opposed to the sulfurs on the top or the bottom. So again, back in those days when I was a postdoc, we together worked on synthesizing nanoparticles of these molybdenum sulfides, thinking that, well, the edges, if these undercoordinated motifs are the ones that are the active ones, we want to get as many of those edges as we can. We made these really small nano triangles. We use scanning tunneling microscopy to characterize them. We found out they were in fact very active. So then when I started the group at Stanford, here are 2 of our early stage researchers, Jabo and Jakob, who started synthesizing all kinds of different formulations, nanowires and mesoporous materials and small molecular clusters. And the goal here was, how do we build more edge sites, more undercoordinated sites into our electrode? And long and short of it is, the more edge sites you put in there, the higher activity you get. So let me show you some of the data. These are very fundamental experiments. We're going to really control the structure, control the edges, et cetera. So this is current density here on the y-axis. The more negative you go, it means the more hydrogen you make. This is voltage on the x-axis. And so equilibrium potential here is 0. So if you hold your electrode at 0 on the scale versus reversible hydrogen electrode, it means that backwards and forwards are exactly equal rate. And so you shouldn't get any net current out of there, which you don't. And then as you tilt the voltage more and more negative, the goal is you want to be able to get this hydrogen to take off as close to equilibrium as possible. Close to equilibrium means the more efficient your catalyst is. You can see as you go from formulation 1 to 2 to 3, we're able to get this to take off earlier and earlier and earlier because we're able to get more and more edges onto our electrode. So that was, we learned a lot working on molybdenum sulfides, really exciting material. Still a lot of activity in that space. They're active, they're stable, they're very good, but we want to broaden our horizons. So we began working. Oh, maybe one thing I'll say is that I just want to point out this metric of 10 milliamps per square centimeter is an important one for fundamental science when it comes to understanding how these catalysts work. So 10 milliamps per square centimeter. I'm going to get back to that number in a sec. But before I do, I was about to say that we broadened our horizons, really looking to a very wide range of ionic compounds, different classes of materials that we thought might be interesting here. And so we went with sulfides and carbides and nitrides and phosphides and phosphosulfides, and really just using a very theory experiment based approach, as I noted earlier, to explore a wide range of possible systems. And what we found is indeed that there are trends in activity that scale with exactly what Beard and Jens had proposed and others some years ago, and that you want the delta G of that hydrogen absorption on your site to be as close to zero as possible. If it binds it too tightly, it gets worse. If it binds it too weakly, it gets worse. So really, we were able to understand a lot in terms of the material side, how to kind of tune that bonding energy and make better and better catalysts. And so we were really excited as we explored a very wide range of space experimentally and computationally. But there is this 800-pound gorilla in the room, or an elephant in the room, or pick your favorite animal. And how do these catalysts actually function in real devices? That was the big question. So we did all these fundamental studies, and did all the kinetics, well-controlled system, but do they actually work? And so that really inspired us to retool the lab. We wanted to continue all the fundamental studies, of course, but we wanted to build new capability to actually fabricate devices, recognizing the water electrolyzers these days a lot of them are based on membrane-based designs. And so we came up with deposition tools and fabrication tools and spray tools to really do these studies, as well as test stations to test these things under a more realistic operating conditions for industry. And so Desmond was among the first in the lab to start doing this with some of our original formulations of sulfides and phosphides and phosphosulfides. So what he did is he kind of reformulated a lot of these materials into ink-based formulations, which then could be leveraged in synthesizing membrane electrode assemblies. Again, this is the construct of modern day electrolyzers. A lot of them are going with a membrane-based design. And so he basically refabricated these things in a system that could then be housed in an electrolyzer hardware, where you can actually flow water in and run the reaction under relevant reaction conditions, which you see here, we were successful at. So this is now, we're looking at voltage on the y-axis, current density on the x-axis. I had mentioned 10 milliamps per square centimeter just a moment ago. Notice that now we're on the order of amps per square centimeter. So real commercial electrolyzers operate on the order of 1 to 2 or more amps per square centimeter. This is the regime that you need to be in. And this is the benchmark platinum iridium case. We have every anticipation that that's the best one that's out there. Indeed, it still is today. Performs really well. And if you wanted to swap out that platinum with some of these non-precious formulations, you can do that, and it still works. You can still get to your amp per square centimeter, which is a huge sign for us. It was very important to recognize that it can actually work in a real device context. And now we've swapped out all that expensive platinum for something cheaper and more available. Now, there is a cost, and the cost is you have to pay about 0.2 volts more in electricity to get there. And again, 10 years ago, those economics don't look so good, but with dropping prices of renewable electricity, now you can ask yourself, is it worth the trade-off to have a lower CapEx system that has less precious metals, or that operates less efficiently, or a more efficient system with higher CapEx? So we can actually do that analysis now that it's a little bit different than it would have been a few years back. Nonetheless, we still think it's important to come up with non-precious metal hydrogen catalysts that work as well as platinum. So we continue on that thread of materials discovery and development, but at least we know it can work in this context. Now, to take it one step further, we wanted to see if this thing would work in a commercial system, a real commercial system. We were making our own home-built membrane electrode assemblies. Here's Mackenzie and Lori, who work together with partners at NEL and Proton Onsite that I mentioned earlier. They sell this water electrolyzer. It's an 86 square centimeter MEA that operates at 400 PSI and 50 degrees C and 1.8 amps per square centimeter. So what Mackenzie and Lori did is they scaled up some of our catalysts and we shipped it over to Connecticut. They integrated it into their system and it worked. It worked pretty much on the first try, which was amazing. Here's the polarization curve. Again, current on this axis, voltage on this axis. Yes, the cobalt phosphide can crank out your 1 amp or more per square centimeter. And you do pay a voltage penalty of 0.2 volts because no human-made catalyst on Earth can still compete with platinum unless it's precious metal. So again, still a research opportunity there, but it works. And then the question was durability. How long would this thing last? And so here's an experiment where we ran it for 1,700 hours plus continuously, and it showed no sign of falling apart. We just happened to end the experiment because the project that was funded through the US Navy had ended. And so that was it, flip the switch, and we wonder how much longer it would have lasted. But just to give you a sense of turnover numbers, that represents about 10 to the 5 turnovers of hydrogen for every cobalt or cobalt phosphide unit in there. So it's clearly pretty stable under these very real, highly acidic, higher temperature, higher pressure operating conditions of a real device. Now, there's much more to be done in that space. We continue onwards, but let me switch gears a little bit and talk about maybe a different design criterion, and that is, can we design electrolyzers to operate with impure water feedstocks? So let me get off the catalyst train for a second and just mention, well, one way to save costs is not having to purify the water. Every commercial water electrolyzer today, it takes in tap water typically, and there's a lot of CapEx that goes into purifying that, basically making millipore level water to then feed into the device to keep it working. If we can work with impure feedstocks, that might obviate those costs, and there's some savings if you could use, say, tap water directly, or even more difficult, seawater. And that's exactly what Daniela and Joe and Adam have been working on, is developing new designs of electrolyzers that can work with impure feedstocks. So we do this work in collaboration with Shannon Butcher and his team at the University of Oregon. And as you can see here, it's a different type of design. It's a bipolar membrane design, and it has all kinds of catalysts in there to do the chemistry that we're asking it to do. And the real key is, can you control ion transport, and can you control these ions, the activity and the chemical transformations involving them as well. And so this is just one example of some of our work here, where every so often Daniela and Joe will head off to Half Moon Bay. It's a really nice place to visit if you're up in the Northern California area. And they collect real Pacific Ocean seawater. All they do is filter it to get the gunk out and then feed it in to this electrolysis system. And as you can see, we've shown over 100 hours of durability. Now, it doesn't operate with the same efficiency as the purified systems do, and there's all kinds of challenges. Ultimately, these things do fail. But this is very promising that we're going to have to redesign the system. But if we can work with impure feedstocks, not only would it make it lower CapEx for these hydrogen producing plants, but also broadens the where this technology can go. It might make it more equitable, especially in places that might not have the drinkable and purified tap water that we all get to enjoy in the United States. Now, another level question is, how do we couple this stuff to sunlight? So sure, you can couple it into the grid, which makes a lot of sense. But what if at some point, now remember, the chemical industry is way bigger than the electricity industry. So we need a lot more electricity if we're going to start powering processes with renewables. So if you do a direct coupling process, there's a lot of advantages to doing that. So the first thing you could ask is, what if I couple electrolyzers to photovoltaics? So here's someone from Lindsay and Jesse and Jiang. Lindsay and Jesse were former PhD students in the group. Jiang was a student with Jim Harris in electrical engineering. And so what we're asking the question is, how would you design your photovoltaic to directly power your electrolyzer? And so it's a really interesting analysis. It turns out that the design criteria that you would look for in PV is very different in this context than what you would use for, say, a PV and utilities solar. So world record PVs out there, in case you weren't aware, about 46% efficient, which is ridiculous. If you ask me how amazing that is, you can collect sunlight and convert 46% of that incoming photon energy into electricity. But if you're going to make hydrogen, there's a big difference, because a photovoltaic, what governs its efficiency, I should say, is how much voltage and current you get out of the PV versus the incoming photon energy flux that's coming through. And in this case, what's important isn't so much the voltage and current output of the PV, but rather how many hydrogen molecules you make for that energy input. It actually changes the direct design criterion a bit. And that's exactly what we did. And so we designed a triple junction 3-5 system that was fabricated by Solar Junction, and combined that not with one, but with 2 water electrolyzers that we made in-house in lab. And I'm not going to go through all the details. We can talk about it later if you'd like. But we were able to demonstrate as an average solar to hydrogen efficiency of 30%, which I think to this day is still a record, not only in the area of solar PV electrolysis, but also I don't know if there's another process I've seen out there that is 30% efficient at taking incoming solar light and converting that into H2, which is of course a much more storable medium than electricity. Now, there's another approach that one can take, and that's combining these catalysts and semiconductors in one construct. There's some work from Mika and Ruben, former PhD students in the group, along with Chase Aldridge and Todd Deutsch and James Young and others at NREL. And the idea here is to take now this is a dual junction photovoltaic and coating it with the right catalyst and protective layers to see if we can get this to work under real solar conditions. And that's exactly what this is. So this is unassisted solar water splitting. This is no wires. Mika would go out to NREL, work with Chase and others to take this fabricated system, some of which was fabricated in NREL, some of it was fabricated at Stanford, and then get it out onto a real rooftop and measure hydrogen production under real solar conditions. This on-sun test demonstrated almost 13% solar to hydrogen efficiency. And very importantly, it also taught us a lot about the durability of these systems under real world conditions. And that's very different than simulated lab light, let me tell you, especially in the middle of January in Colorado in the mountains. So I'm not going to dive deeper into that, except for to say that durability is a major area of effort in this particular space. All right, with that on hydrogen, this is where I wanted to put most of our time and attention. And then we can talk a little bit about, build off of that knowledge and talk a little bit about carbon-based chemistries and nitrogen-based chemistry. Basically, this is hard, this is harder, this is the hardest of the three. And the nice thing though is that you can build on these. So basically this hydrogen is kind of the flagship in this whole concept of renewable fuels and chemicals. Basically about 300 gigawatts, I'll say it again, 300 gigawatts worth of electrolysis projects, green hydrogen projects have been announced. So really over the next decade, I think there's going to be a lot more renewable hydrogen coming onto the scene. And I look forward to the day when we can say that about carbon-based chemistries and nitrogen-based chemistries too. I think we will get there. It'll be, a few steps behind, but the key thing is that we can learn so much from the hydrogen space, which again is the flagship. So let's talk about carbon dioxide reduction. Wouldn't it be lovely if you could just grab CO2 from the atmosphere and convert that into carbon-based products through an electrolyzer? And the short answer is you can do this. It's just really hard. And you have all the complications that the water splitting systems have and so much more, because really steering selectivity is really tough. You throw CO2 and water in an interface, you start breaking bonds and making bonds. What are you going to make? Some catalysts could care less if the CO2 is around and let us make hydrogen anyhow. Others will make C1 products like these. Others will do multi-carbon products and do some CC coupling, either making hydrocarbons or oxygenates. Just a lot of possibility. And so it's just a lot of room to understand. We need to understand how to design these systems and then build them once we can develop catalysts that are selective to make the one product we want and not the ones that we don't. And so I want to just kind of recognize a very large collection of scholars that have been contributing to this space. And I'll kind of note them in a moment as we kind of talk about different areas that we've worked in. But let me start with some techno-economics, kind of like we did with the hydrogen. Hydrogen techno-economics, shows opportunity, but still a ways to go. But I think we can get there. Same with this. This techno-economics is basically looking at CO2 electrochemistry, making carbon monoxide versus, let's say, ethylene. Every product has its own market, its own price point, its own constraints. And the short answer is, if electricity cost is cheap enough and your energy conversion efficiency is high enough, you can find yourself in a profitable regime where you can actually compete against the conventional processes that are out there. A lot of assumptions in these models, but good to know that if we're successful in the lab, we have a chance to actually get this successfully implemented at the commercial scale. Not to trivialize how tough that is to transition it along, but at least these techno-economics give us a sense that it might be possible. And we first started getting into this space. This is some work from Kendra, Natasha, and David. Kendra and Natasha are some of the early stage graduates in our group, and David as well. The two of them ended up starting a company called 12, now commercializing CO2 electrolyzers. And in some of their original work, as you see here on copper catalyst, one of the first things that we intended to do is just to understand, what does the reaction network look like for CO2 reduction on copper? And it was known that it could do a lot of chemical transformations to make products of interest, But our goal here was to really identify and quantify these things to the best extent possible. What we saw were 16 different molecular products emerging from the surface. And as you can see, voltage, and these are the current densities for different types of products, you can see that a lot of these products emerge kind of at the same time, which basically means it's a big mix. And separating mixtures is not an easy proposition. It takes a lot of energy. And so really copper is kind of this type of a catalyst that works like this is not going to work so well from an industrial perspective. We need to figure out how to steer that selectivity. And so this is some work from Stephanie and Chris, who really put a lot of time thinking deeply about the chemistries involved. And there's a lot of fantastic work out there. This is just a diagram to show you if you throw CO2 at a surface, you start hitting it with protons and electrons as depicted here. Yes, you can start making transformations to all kinds of intermediates and ultimately some products. It could be like a methane or a methanol or CC coupled products like ethylene or ethanol, et cetera. And very complex diagram. We're still learning about this. There are some things that we do know, some things that we don't know. One of the things that we do know, or at least the community seems to agree on, is that carbon monoxide is a key intermediate. So if you want to make multi-carbon products, for instance, going through carbon monoxide is the likely intermediate here. Still major challenges. How do we suppress hydrogen evolution? How do you favor multi-carbon products over C1 products? Can you favor multi-carbon products or multi-carbon oxygenates over hydrocarbons? How do you make a single desired multi-carbon oxygenate? It's really tricky because as you imagine this pathway, a lot of the mechanistics are similar for different products. So how do you steer the selectivity when they have so many common intermediates involved? So a lot of challenges to unpack here. And as an aside, almost, I want to just kind of bring something up for some of you who might be working in thermal heterogeneous catalysis. There's so much to learn from both of these communities. Oftentimes you go to an ACS meeting, electrocatalysis stuff here and thermal heterogeneous catalysis stuff there. Communities are oftentimes very segregated. But I think there's just so much opportunity for those two communities to learn from one another, because at the end of the day, this reaction is the same, right? Carbon dioxide electroreduction, you put 2 protons and 2 electrons on a CO2, you make CO. Reverse water gas shift, you throw hydrogen in CO2 and you can make CO. So there's a lot to learn, and that's something that we were very interested in trying to bridge some of those divides. And I long wanted a catalyst that I could synthesize where I'm like, here, there's a powder catalyst. I'll put half of that catalyst in the electrochemical cell and the other half in a packed bed reactor, and run these two reactions and actually see apples to apples, what do they have in common and what's different. And it took a while to get there, but we got there. And David Koshi, a recent graduate from the group, working together with Sindhu Nathan, who's also graduating at Stanford right now, Cindy and Stacy Bent's group, worked together on this. And the idea is to look at nickel nitrogen doped carbons as the catalyst motif, which looks a little something like this. These are single sites of nickel embedded in carbon. We've done lots of characterization. I'm not going to have the time to dive into to really prove to ourselves that that's what we've got, including synchrotron-based studies. And the reason why this turned out to be a really interesting motif is because we found that this motif was still present there, whether we ran it electrochemically or with thermal heterogeneous catalysis. So it was kind of a reliable, resilient catalyst motif that didn't change to the best of our ability to characterize before and after a reaction, which allows us to draw some connections between those two disparate, seemingly, areas of catalysis, thermal and electro. So here's the data to kind of show a reverse water gas shift, running it as you would in a packed bed reactor, several hundred degrees C. You can see that it's very selective for making carbon monoxide. Take that same catalyst from an electrochemical cell, give it some voltage, and indeed, under a lot of these regime, we're seeing very high selectivity to CO. So now we know that it works. What do the kinetics look like? And so these are the kinetics. So now you're looking at, this is the reaction rate of how many carbon monoxide molecules electrochemically you produce. And this is just a retuning of the voltage scale using overpotential on the x-axis, just really fitting, as we would know, the Tafel equation or the Butler-Volmer equation. And you can see that data here. This is the reverse water gas shift chemistry, again, is a function of temperature. We can see how the reaction rate changes based on the Arrhenius equation. No big surprise that Arrhenius and Butler-Volmer have a lot in common, of course, both exponentials. We do measure different activation energies for these two processes, which is really interesting. And also really interesting too is if you look at the y-axis here, the turnover frequency is orders of magnitude higher than it is for the temperature driven process, which might not be so expected. So we try to figure out, like, okay, what can we learn from all of this? So taking all these kinetics, recognizing that the Arrhenius equation and Butler-Volmer are both exponentials, and they're just different representations of driving forces for these chemistries, we said, can we non-dimensionalize the driving force? And so that's exactly what we did. We basically came up with a parameter called D, which is a dimensionless driving force that is portable to both the electrochemical world as well as the heterogeneous catalysis world. And we take all of this data and you can plot it up onto a single chart. What you find is that the reaction rate, the amount of carbon monoxide produced per nickel per site per second, it fits almost exactly on the same line, whether you're on the thermal heterogeneous catalysis regime or the electrocatalysis regime. So it's really just to say that what the differences we're seeing predominantly are due to massive differences in driving force. Effectively, put your hand on voltage and start cranking the knob on voltage. That is a way bigger change to the landscape, to the energy landscape, than changing, say, temperature in this experiment. So that fits. It doesn't necessarily explain the difference in the activation energy. And so we think that a lot of this difference is, in fact, coming from solvation differences right at that interface, that when you have an electrified system in an electrochemical cell, you have anions, you have cations, you have water nearby. It's a very different environment than you do in the reverse water gas shift. So a lot more that we can dive into here, but I just want to present this as an opportunity to try to bridge these different communities, whether you're into biocatalysis or molecular catalysis or surfaces or, or of any type of catalysis. We really need to be trying to unify principles amongst our different fields. And I think that's where we're going to be able to get the most knowledge to understand how to make bonds and break bonds the way that we desire. Now, kind of getting back on the train of what do you at the end of the day, what do we want to do? The eye on the prize is we want to convert carbon dioxide into useful products. And so I just want to give a couple examples of what we've learned in that space and how we can make use of, for instance, CO produced sustainably. So I just showed you an example of making CO using that nickel-based nitrogen catalyst, carbon-based catalyst. We can do it thermally, we can do it electro. And let me just kind of dive into one way of using carbon monoxide as just making a really high surface area copper-based catalyst. This has huge advantages, it turns out, versus a flat catalyst. And yes, there's a lot to be said for kind of special sites and uncoordinated sites and things like that. But it's actually, there's something that's really important here. When you have a higher surface area electrode, you can operate at less negative voltages because you've got so much surface area that you can get to your reaction rate at lower voltage. And if you're operating at lower voltage, that'll change the selectivity of the products that you're making. And so this is exactly what we see. So now in this case, we're doing carbon monoxide reduction on this high surface area copper using an alkaline electrolyte, which if you're doing CO reduction, you can choose alkaline, acid, neutral. When you're doing CO2, of course, the CO2 will equilibrate, so it doesn't give you much flexibility on the pH range that you can use. So we're kind of starting to throw everything in the kitchen sink at this. And the interesting thing that we saw, these are results from Lei Wang and Steph and Chris, is that we didn't see 16 different products, which is what we saw for the CO2 reduction experiment in neutral conditions. We really, at these very modest voltages, negative 0.23 volts. The other data I showed you from Kendra, Natasha, and David was like a negative 1 volt. Okay, so you're saving lots of voltage and you're getting much better selectivity. In this case, really the three products that we see are acetaldehyde, acetate, and ethanol. So this is a way of kind of steering selectivity of the reaction with a high surface area electrode that lets you work at very modest voltages. We're using carbon monoxide as the reagent instead of CO2 because we know we can go from CO2 to CO using other catalysts. And we're doing this in an alkaline environment. Now, if you want to crank up the reaction rate, of course, you got to go to more negative voltages to do that, and you will sacrifice selectivity as a result. It's not uncommon in catalysis. So these are definitely some things to think about in terms of steering selectivity. Still with a copper catalyst, if we start tuning the copper catalyst to something different, we can get even more benefit. And that's exactly what we worked on based on theory. Silver copper seemed like a pretty good system. And so we made some flat foils of copper silver just by a galvanic exchange process. You basically dip your copper in silver nitrate, you'll get some silver decorating the surface. We did that with flat films. We did that with these nanoflower high surface area materials that you just saw. And then you can take a look at the selectivity. Now, over 90% of the CO2 reduction is going to one product. This happens to be a multi-carbon oxygenate of acetaldehyde, a little bit of ethanol, a little bit of acetate, a little bit of ethylene. And we still, though, by the way, have a hydrogen issue. We're still making hydrogen, and that still remains an unsolved problem if you want to do CO2 electrolysis. You probably don't want to make H2. You want to make H2, you just made a water electrolyzer in the first place. But this is all really a way of saying that we can steer this chemistry, this very complicated diagram. We went from CO all the way to acetaldehyde by taking all these different kind of approaches in concert, working with one another to get the mechanism to go where we want it to go. Now, there's still, I did mention with our catalyst to get you from CO2 to CO, but how do you build devices to do that? And here's some work I wanted to show from Sarah and Dave. Sarah was a visiting PhD student, Dave was a postdoc in the group. And what they started doing is started building devices. Just like I was showing them with the hydrogen side, we were very interested in not just making catalysts, but also showing how they can function in a real world system. So that's what they started doing, is building membrane electrode assemblies for CO2 to CO catalysts. In this case, it was silver zinc system that they were interested in. And so they built it. And here's just some data showing you the performance of this membrane electrode assembly. It's operating at 200 milliamps per square centimeter. We're feeding in humidified CO2. And you can see almost 100% of that CO2 is getting converted into carbon monoxide. That's the Faraday efficiency for carbon monoxide up here. The voltage efficiency, the energy efficiency, about 35%, so not nearly as efficient as the water electrolysis systems, which is exactly what we would expect. At least our reactor is working the way we like. It's operating at realistic current densities and making the product that we want selectively. And then we said, well, now that we can make CO2 to CO, how well does this couple to other processes? Can we make some cascade scheme of reactors or tandem scheme? And we wanted to get out of our comfort zone. And so we looked at biology and microbiology, specifically working together with Electrocatalysis, Alfred Sporman, who's a colleague of mine in chemical engineering. And they work on a number of different microbes, including Clostridium autothanaginum, which is a microbe that can take in CO and make you some ethanol and some acetate. And so the question we had is, well, is our reactor effluent here biocompatible? So we tested that out. So Frauke brought the microbes to the lab. Our reactor, we fed it into CO2. We ran it at a single pass conversion of 25%. So 25% of that CO2 came out in the form of CO. About 10% hydrogen production, like I said. There's generally always a little bit of hydrogen. And then, of course, the balance of CO2 is going into this fermenter. And indeed, it worked. It turns out that we were able to convert about almost 100% of the CO that came out of our reactor and into this bottle was consumed, was taken up by the microbes, and it made exactly what we expected, acetate and ethanol. And when we ran the control experiment without the carbon monoxide, the metabolism, of course, slows down tremendously. It makes a little bit of the products, but not much at all. So really, this is just an example of why I think we can all work together no matter what area of chemical transformations you're thinking about. I think coupling these things and integrating these things is going to be really important to make all the products that we need. There's 70,000 different molecular products across the globe. Some of them are going to be easier in a one-pot synthesis, and some of them might require more complex reaction schemes. Now, in my last really like 2 to 3 minutes, I just want to say a few words about ammonia. It's the toughest of the bunch. I get to work with wonderful people here located at SUNCAT, also across the Atlantic in Denmark at the Technical University of Denmark. And what are we trying to do? Is we're trying to complement the Haber-Bosch process. Haber-Bosch is amazing. You feed in nitrogen that came from the air, hydrogen that came from steam methane reforming, and this thing runs at very high temperatures, very high pressures, and converts that nitrogen into ammonia. That ammonia, of course, goes into the ground as a fertilizer, and then we eat the crop, or we eat the animal that ate the crop, and that's how we get fixed nitrogen in our body. So have to fix nitrogen in your body, touch this iron nanoparticles in some Haber-Bosch facility somewhere, not too far, probably. Now, there's a lot of challenges. It's a great process. It's actually pretty efficient, very productive, 180 megatons a year. But among the major problems, it's not sustainable, obviously massive emitter of CO2. And then another issue is that because these are centralized facilities, the distribution is actually not very good. We pay way less in the United States for fertilizer, about a factor of 5 to 6 less than they do in Central Africa. It has nothing to do with making the ammonia, it has to do with the distribution system. Another problem is that lands oftentimes get over-fertilized, and it turns out that ammonia, that fixed nitrogen ends up running off as a wastewater contaminant, or as a contaminant into streams, making them waste, as opposed to going into the crop where they were designed to. So kind of a just-in-time delivery process would be way better. Imagine solar cells coupled to some electrolyzer that was breathing nitrogen from the air, just like you and I are, right now and converting that into ammonia, and you size your system to make just the right amount of fertilizer. And of course, this system only works when the sun is shining and when there's water present, which is exactly when the crops want it. Now, as lovely as this looks, it's really hard to do. And there's theoretical frameworks that help us understand that. The long and the short is that any catalyst that is capable, electrocatalyst, of converting nitrogen to ammonia will basically prefer to make hydrogen by 1 billion times faster. So that's not going to work as a process of only 1 in a billion molecules one year after. So I just wanted to show you a different approach, and that's what we're working on. It's really non-aqueous chemistries is what I would say is the big theme of what we do. Here's one example of non-aqueous chemistries. If you go non-aqueous, that's how you can mitigate hydrogen production versus ammonia production. And so what we do is we take a molten salt, and in this case, lithium hydroxide, potassium chloride, and we use that renewable electricity to plate lithium metal. Then we expose that lithium metal to nitrogen. You form a nitride. You dump that nitride in water. You hydrolyze it to make lithium hydroxide back again, and your ammonia. And then you take that lithium hydroxide and move it right back. So this is a cyclic process by which we've shown that you can get 88% of the electrons going into ammonia. Now, it does require a lot of voltage because electrodepositing lithium is like a 4-volt plus chemistry. But we did the analysis, and if you have a typical agricultural field, 1 hectare, which is 100 kilos which requires 100 kilos of ammonia per hectare per year, you had a process like the one I just showed. This is how much agricultural land you would need to consume with your solar cells and your technology to produce a yearly amount of ammonia, of fertilizer for that land. So this is what the kind of techno-economics look like from the farming perspective, but it's definitely too expensive, and that's why the process I just showed you. How do we make that cheaper and cheaper to compete against conventional processes for ammonia production? Last thing I'll say, and then we'll wrap it up, is that for those of you who might be interested in ammonia, it is really easy to fool oneself thinking that they made ammonia, but it's really just coming from adventitious sources around us. There's so much ammonia in our ecosystem because that's what we use to live, that we really need to be very rigorous about quantifying and identifying and knowing that if we do know we made ammonia, that we want to be able to say that it came from the N2 that we fed it, as opposed to from adventitious sources. Just letting you know, a lot of what we've been working on in space development methods and protocols, encourage you to take a look at those if you're interested in working on ammonia chemistry. So with that, I'll just summarize with one simple sentence. I think there's a lot of promise in emerging pathways for the sustainable production of fuels and chemicals. I want to thank my research team for all their contributions. Thank different funding agencies who have contributed to different elements of the talk today. I thank you all for the invitation and the opportunity to engage. I'd be happy to answer any questions. Thank you all so much.
Thank you so much, Professor Hermiou. If you would like to ask a question, please use the Q&A function. I have one to start with, actually. It's on slide 7. My camera's not working right now. Sorry about that. You talked about how the renewable electricity target is already achievable on smaller scales. Among these other targets that you listed here, which one is the furthest? Or which one do you think needs the most development?
Goodness gracious. Well, so carbon capture, the cheapest carbon capture we have out there is about $70 a ton, but that's not coming from air, that's coming from point sources. So that's just an example of kind of the closest there. Energy storage, gigafactories and whatnot are about an order of magnitude more expensive than this, like $100 kilowatt hour to $200 kilowatt hour, depending on how you want to define your system. And then the electrolyzers out there, hydrogen, like modern day hydrogen electrolyzer plants are around $1 to $1.50 per kilogram. So, none of these I would say are, and these are all small numbers, like $1 a kilo versus 20 cents per kilo. Doesn't sound like it's off by that much, but it's really hard to get down that cost curve. And remember, the product cost here is, we're aiming, a lot of these products are like 50 cents a kilo or $1 a kilo. So kind of every penny counts.
Thank you. I didn't see any other questions. I had a couple more, actually. I was really interested in, I see a couple just popped up. I'll let other people have a turn as well. Luca asked, can you talk about the implementation of the molten salts ammonia production process into a real device? What temperature and pressure does the process operate at?
Yeah, thank you for the question, Lucas. So that system operates at ambient temp or ambient pressure, but at about 400 degrees C. And I think that's okay from a decentralization perspective. It's actually much tougher to decentralize high pressure. It's a lot easier to decentralize higher temperature. 400 degrees C is not that bad. And so, we have a team, actually, some of the folks in the lab who are working on that launched a company called Electricity. And so they've been exploring different means. I can't talk in detail about their approaches, of course, but it's certainly not easy, but it's also not impossible.
Thank you. And then Plummet asks, what could be optimal scale of deployment for electrochemical Haber-Bosch process? Can it be sustained as distributed manufacturing?
Yeah, that's a great question, Plummet. I look forward to hanging out with you. It's been a long time. I would say that the challenge, there are a lot of challenges to the distributed systems, but again, I think those things can scale by tens of megatons without a problem if we can solve the technical issues involved. There's a lot to unpack in that sentence, but what I would say is two things. I think in the future, we do want the centralized facilities. I think the centralized facilities make a lot of sense in places with good distribution networks. And thankfully, Haber-Bosch is one of those processes that relies heavily on hydrogen, which means it has a huge CO2 footprint today because 97% of all hydrogen comes from fossil. But if we can put in renewable H2, voila, we've kind of solved that problem. The challenge is generating distributed systems, centralized systems in all parts of the globe. A lot of issues with that. And I think there, the decentralization gives us the opportunity. If it's a factor of 6x more expensive because of distribution, then that means that those standalone systems can be much more expensive than the current Haber-Bosch technology and still actually have a market to go into. So I think that market is on the order of tens of megatons per year.
Thanks, Tom. And I see a question from Andrew. In regards to capital costs for the stacks for H2 production, what share of the cost is for platinum, what share is for iridium?
Great question. So currently the precious metals account for approximately, it's very modest currently, it's like 5% of the total cost of the electrolyzer, which doesn't sound like a heck of a lever, but it is. They're all important levers because there's no one lever that'll do it. But I'll tell you the reason why 5% is actually much bigger than 5% because current electrolyzers, the balance of systems cost is very expensive. The manufacturing is very expensive. And as scales increase for the production, the cost of the balance of systems will continually decline. But the price of platinum, the price of iridium is fixed. And so it'll go from 5% to 8%, 10%. That slice of the pie will just keep getting bigger and bigger. And so the more we can do to minimize precious metals, the better off we're going to be able to reduce costs in a substantial way.
Okay, thanks. We'll do one more question, so we have a minute left. Generally, companies are okay with higher CapEx and want lower OpEx. Correct me if I'm wrong. How can we convince them to accept the trade-off of lower OpEx for higher CapEx, cheaper catalyst, but more voltage?
Yeah, that's a great question. I think that's also why, so I don't know if that's universally true. Let me just say, I think what is more important is what the total cost is and having certainty in the operational expenditure. So right now, hydrogen, a big chunk of the cost of making hydrogen today is the cost of natural gas, right? Which is obviously anything involving oil and gas, especially these days, is highly volatile. So if you can lock in prices for an operational expenditure and you have certainty around that, I think there's no problem in that. With that being said, lower CapEx is always a good thing, and not only for the sector as a whole, but if you're an individual company looking to launch your product, always looking for a way to lower the CapEx because that's what people are going to purchase. And so, yeah, there is lots of opportunity for the precious metals to try to compete head to head against them without using precious metals. I think that will remain a key challenge.
Okay. Thank you again for talking today. I think that was a really inspiring lecture for everybody, very educational. And hopefully we'll see you down here in Irvine sometime too.
Oh, I look forward to it. Thank you, Jenny, for hosting me. Thank you all for attending. And I look forward to opportunities to engage further. Take care. Have a great afternoon, everybody.